Hello everyone, welcome to another email security webinar. This webinar is a collaboration between Zimbra and Randy Liker from Skyway Networks. My name is Barry de Graaf and I am Channel Evangelist at Synacor. This is our fourth webinar that helps you maximize Zimbra email security. In our previous webinars, we have talked about SPF, DKIM, DMARC and more, and the recordings and slide decks of these webinars can be found on the Zimbra blog and the Zimbra YouTube channel. In today's webinar, we will explain DNSSEC and how it can improve privacy and confidentiality for email. During this webinar, you can ask questions via the Q&A panel, and I will try and answer them on the fly. Some questions we may also discuss live during the webinar. Today's webinar is recorded and will be published on our blog and YouTube channel, where you can find it for future reference. And with that, I would like to give it to Randy, our expert in email security.
Well, thank you everyone for joining us today for this fourth episode in the Zimbra webinar series that is all about email security. Today we'll be focusing on the topic of DNSSEC. So for those of you who are joining us on this webinar series for the first time, as a brief introduction, I am the president and CEO of Skyway Networks. Skyway Networks is an email service provider specializing in Zimbra hosting and consulting. We also provide a variety of cloud hosting services, including software development. And I've been personally working in the IT industry for 26 years, and of that time, 23 of those was Skyway Networks. And I've been working with Zimbra servers dating back to Zimbra version 5.0. As an overview of today's topics, I'll take you through a brief overview of DNS and introduce you to what DNSSEC is. This will be followed with a discussion of DNS security vulnerabilities to be aware of, then an introduction to DNSSEC concepts you need to know. This webinar is being recorded and will be posted for later replay on the Zimbra YouTube channel at the URL you see at the bottom of the screen. So this webinar discusses solutions to defend against a diverse range of threats, including phishing, eavesdropping, information leakage, man-in-the-middle attacks, security downgrade attacks, and online reputation damage. The next upcoming topics in the series will be a discussion of demystifying how TLS works in relation to providing email encryption, along with a discussion of how you can use the DANE standard for addressing weaknesses inherent to how the certificate authorities operate for issuing SSL certificates. As shown on screen, earlier episodes have already covered many important security topics, but in case you missed any of these, again, they are on the Zimbra YouTube channel for viewing anytime at the URL on the slide. So with that introduction out of the way, let's get started on today's topic of DNSSEC. The domain name system, more commonly known as DNS, is something that we all depend on every day, and it was introduced about 40 years ago in 1983. Similar to other early standards on the internet, DNS offered no consideration for security. Subsequent revisions to the DNS standard over the years have since fully addressed the shortcoming, but only a minority of domain owners are taking advantage of these improvements. When compared to other early internet standards like SMTP and HTTP that have evolved over time to include widely used secure configurations, DNS has really severely lagged in security, and many domain name owners still today continue to operate their DNS servers in a manner not much different than the original insecure DNS standard from years ago. This leaves their DNS records open to being overridden and spoofed at will by an adversary. So if you consider for a moment all of the services in our online lives that are built on top of DNS and depend on it to operate without fail, it is puzzling that such a crucial network service is still widely operated with close to zero security. The stakes to secure DNS become even higher when you consider how email servers depend on it for even the most basic functionality, like delivering messages from one server to another. Then there are all the other security standards built upon DNS as a foundation. These include topics covered in previous episodes of this webinar series like SPF, DKIM, DMARC, MTSDS. And without secure DNS, not only is basic email server functionality open to exploitation, but it can also readily neutralize and invalidate all of these security standards just because those standards presume that DNS has already been secured. This is a common oversight that many organizations make, in that they deploy SPF, DKIM, and DMARC and think they are secure, when in fact they've still failed to deploy DNSSEC. And these standards are actually intended to be used together. By the end of this webinar, you're going to have a new perspective of how important DNS security is and why it needs to be protected. So what is DNSSEC and why do you need it? Well, DNSSEC is an acronym for Domain Name System Security Extensions. And it was introduced back in 1990. That was the first major change to DNS since it debuted on the internet in 1983. And DNSSEC basically strives to provide built-in security for the first time. But DNSSEC got off to a very slow start as it had close to 0% adoption online from its introduction in 1990 to as recently as 2008. The turning point, however, was a key event in 2008 that initially brought awareness to domain name owners of why DNSSEC is needed. Unfortunately, the insights learned from this event were not shared by all and continue to be relearned since then, following repeated successful attacks against DNS since that time. So DNSSEC sets out to accomplish several ambitious goals. The first goal is to provide DNS users with a means to authenticate that the answers they receive for a DNS query originate from a domain name owner's legitimate DNS server and not an adversary. A second goal is to provide a means to verify the integrity of a DNS answer to a query to prevent tampering and DNS cache poisoning. Now, I will elaborate a little bit later what it means to poison a DNS cache. And then the third goal is to authenticate a non-existent domain answer to a DNS query. At first glance, this may seem like an odd thing that needs to be secured, but what it actually accomplishes is it prevents an adversary from creating new subdomains without a domain name owner's knowledge. And in a later slide, we will look at an example of what this means. And finally, a fourth goal of DNSSEC is to build a secure foundation upon which other security standards that depend on DNS can be used. As mentioned in an earlier slide, if an adversary can tamper with the DNS answers for your domain name, then they can readily neutralize and invalidate the security provided from other standards, again, like SPF, DKIM, DMARC, MTSDS, and DANE. There are, in fact, proposed standards in the works that rely on DNSSEC to provide authentication for services like voice over IP, text messaging, SSH key management, and more. So as a brief example, consider the case of SSH key management. A long-standing challenge has been how to reliably determine if the first connection to a server can be trusted when using SSH. Most SSH client apps will simply ask the user if the server's SSH key should be trusted on the first connection. Now, one of the new proposed standards seeks to solve this by storing SSH public keys on DNS servers that have been secured with DNSSEC. This would provide independent proof upon first connection that a server's SSH key can be trusted without needing to prompt a user to make a judgment call on their own, just by doing a simple DNS query. This is just one of several improvements anticipated to be built upon DNSSEC in the near future. But it's also important to mention here what DNSSEC does not offer. DNSSEC is not designed to provide data confidentiality. In other words, DNS queries and answers are going to still be sent in clear text across the internet without any kind of encryption. Now, this is intentional as it preserves backwards compatibility with DNS servers that do not yet support DNSSEC. And this makes sense because DNS has always been about serving data that is considered publicly accessible to any host on the internet. Now, till 2008, DNS security was largely ignored by many domain name owners, despite DNSSEC having been a standard for almost 20 years at this point in time. But this began to change thanks to a security researcher named Dan Kaminsky. In April 2008, Dan noticed that customers of a growing number of internet service providers, most notably Earthlink and Verizon at the time, were intercepting the DNS queries of their customers and forging the DNS answers. This meant that when a customer entered a domain or subdomain into their web browser that should normally return a non-existent name or site not found or similar error, those internet providers were instead forging the DNS answers with IP addresses of the service provider's own advertising servers. So Dan determined that this was possible because the service providers were taking advantage of weaknesses in DNS that allowed these forged answers. But more importantly, the same weakness was readily exploitable by adversaries too for conducting phishing schemes. Then in July 2008, Dan discovered an even far more serious vulnerability that affected nearly all DNS servers on the internet. Using a surprisingly simple attack, Dan was able to repeatedly query any given DNS server he wished to target, and within a short period of time, he discovered he could effectively poison that DNS server's cache. This means that for any domain name on the internet that Dan wished to target, he could force a DNS server to serve out any DNS answers to users that he provided, rather than the legitimate DNS answers from a domain name's owner, all without gaining any access to those DNS servers being abused. As an example, if Dan had wanted to change the IP address for google.com, he could target a given internet provider's DNS server used by probably thousands of those providers' customers and route all of those providers' customers trying to reach google.com to a web server under his control. Unfortunately, Dan is one of the good guys, and he opted to use his skill set for good and proactively worked with several DNS software vendors at the time to develop patches that make this attack more difficult to accomplish, but not impossible. This vulnerability still remains possible today for adversaries with sufficient resources when either the domain name owner or the operator of a DNS caching server have not yet deployed DNSSEC. The simplicity of these exploits in 2008 brought new attention to just how easy it was to poison a DNS server's cache and to manipulate answers to DNS queries. This began to finally raise awareness among domain owners and service providers of the importance of using DNSSEC. So let's do a high-level overview of one type of DNS cache poisoning attack to better understand the nature of this vulnerability. Now, DNS cache poisoning can be summarized as a four-step process. In this example, the adversary wants to target the customers of an internet provider called ProviderCo, and specifically wants to take control of the Zimbra.example DNS records that ProviderCo has cached in their Zimbra.tech DNS records that they have cached in their DNS servers. This means the attacker will be able to redirect any traffic intended for Zimbra.tech or its subdomains to destinations of the adversary's choosing. So for step one, to get started, the adversary does some basic reconnaissance by performing public whois lookups for Zimbra.tech and figures out the name of the DNS server, which in this example is ns1.zimbra.tech. Next, the adversary attempts a DNS zone transfer from ns1.zimbra.tech to download all the DNS records. But this rarely fails because, fortunately, many DNS servers will prohibit this. So the adversary next resorts to educated guessing by performing queries for many commonly used names that might be set up for Zimbra.tech, basically to effectively walk the zone, or in other words, discover as many DNS records as possible for Zimbra.tech. So the adversary will use this guessed information to clone the DNS records for Zimbra.tech on his own DNS server, but instead will alter those IP addresses of those cloned records to direct traffic to a server under his control. So in step two, the attacker sends a DNS query for a subdomain the adversary owns called www.attacker.example to ProviderCo's DNS server. Since ProviderCo's DNS server does not know the IP address for www.attacker.example, it does a recursive DNS lookup. This means that ProviderCo's DNS server is going to contact the adversary's DNS server to ask it for this information. So instead of receiving an IP address from the adversary's DNS server for www.attacker.example, ProviderCo instead receives an empty answer, along with a referral to ns1.zimbra.tech for any future DNS lookups for the attacker.example domain name. It looks very similar to what you see on the slide. So this also includes a new IP address provided by the adversary for ns1.zimbra.tech of 10.10.0.2. And this is the key bit here, because recall from the prior slide that ns1.zimbra.tech is the legitimate DNS server the adversary found using a whois lookup for the Zimbra.tech domain name. But since the adversary has provided a new IP address here for ns1.zimbra.tech, ProviderCo is now going to add this to its DNS cache, effectively overriding the previously cached good IP address for ns1.zimbra.tech with the bad IP address provided by the adversary. Going forward, whenever any of ProviderCo's customers do a DNS lookup for Zimbra.tech or any of its subdomains, ProviderCo will now send all of those DNS queries to the adversary's 10.10.0.2 IP address. And this now allows the adversary to basically create any DNS records he would like for Zimbra.tech and its subdomains, thereby completing the corruption of ProviderCo's DNS cache. Now, as this is not bad enough, it actually gets worse. The adversary learned during the recon conducted in step one that there is a Zimbra server called mail.zimbra.tech. So the adversary sets up a new Zimbra server on his own hardware using the same mail.zimbra.tech name, but maliciously configures it to capture and store all user logins it receives. So the legitimate owner of mail.zimbra.tech has an SSL certificate set up to prevent eavesdropping of this login information. But just by poisoning provider code's DNS cache, the adversary can likewise easily forge the SSL certificate for mail.zimbra.tech too. As a result, the real users visiting mail.zimbra.tech to log in to what they think is their real Zimbra server will not see any security warnings, even though the zimbra.tech domain has been effectively hijacked. Now, this is because SSL certificates are not designed to provide any protection against domain hijacking or DNS cache poisoning. Instead, web browsers and email clients mostly rely on DNS queries to check if a hostname in the SSL certificate matches the name it gets back from a DNS server. So in effect, any security provided by an SSL certificate is instantly neutralized. Likewise, the adversary can publish fake SPF and DKIM and DMARC and MTSDS records too, potentially for conducting a range of follow-up attacks, perhaps by personating legitimate users on the Zimbra server. This allows him to send email to those users' contacts since he now controls all of the DNS lookups for Zimbra.tech at provider code. Now, so for the sake of full disclosure, it is important to understand that this is a simplified illustration of just a single type of DNS cache poisoning attack that could be carried out, while in reality there are a number of additional steps that would need to take place for such an attack to succeed. However, this example does illustrate just how crucial it is to protect your DNS records from unauthorized changes, including those caused by a DNS cache poisoning attack. Now, while there are additional safeguards built into most modern DNS servers to make DNS cache poisoning difficult, these safeguards do not make cache poisoning impossible for determined adversaries. But if the domain name owner for Zimbra.tech and provider co had both deployed DNSSEC on their servers, then all varieties of DNS cache poisoning will always fail. Now, one of the several reasons for this is because in this example, provider co could have used DNSSEC to authenticate if the adversary's provided answer for ns1.zimbra.tech should be trusted or not. Now, when a DNSSEC authentication fails, provider co would consider the DNS answer bogus and just immediately discard it. And this would effectively have defeated the DNS cache poisoning attack from the start. So you may be wondering what motivates an adversary to hijack the DNS records for a domain name. Now, there's a couple of common themes that typically emerge. One reason is just simple advertising. If a user searches for a domain name that does not exist, rather than returning a server not found error to the user, instead, a page is displayed offering to sell the user the domain name. This is not as common as it used to be, but it may still occur by some service providers. Now, phishing and click fraud is by far the top reason for DNS record hijacking. If I am the adversary and I can poison the DNS cache of at least one or two large service providers, then I can send out a follow-up phishing email campaign to those users of those same providers to entice them to click and direct them to servers under my control for any number of purposes, like distributing malware or harvesting login credentials. Now, censorship may not be an obvious reason for DNS hijacking, but there are at least several countries with repressive governments that frequently forge DNS answers to queries to prevent their citizens from accessing certain internet resources they deem undesirable. And hacktivism and website defacement are sometimes the goal to make it seem that a website was compromised, when in fact the website suffered no compromise at all. Instead, it is just the users of a particular service provider with a poisoned DNS cache that see a defaced website message, typically hosted on an adversary's web server, rather than the expected legitimate website. Now, Google, of all people, have experienced this multiple times in recent years with their country-specific homepages seemingly having been defaced around the world. Now, when this occurred because adversaries had obtained no access to Google's web servers, but instead they were successful at poisoning those DNS caching servers for large providers or large service providers in those countries. And finally, we saw in the prior example with DNS cache poisoning, it can be quite effective for stealing login credentials from users on a large scale. So now that you've seen some of the bad things that can happen when domain names are not secured with DNSSEC and DNS servers are not performing DNSSEC validation, let's now get into the concepts of what you need to know so you can deploy DNSSEC to start protecting your domain name and thereby protect your Zimbra server from abuse. So with DNSSEC, The familiar DNS resource records you've worked with many times in the past, like A, Quad A, NS, SOA, CNAME, text, pointer, and serve records, all work the same. Just like they do actually on a server that is not configured for DNSSEC. So nothing changes there. However, what DNSSEC does add is several new types of resource records. Now, rather than defining all of these new record types on this one slide, I think the best way to explain these is to provide the context of where they are used. And this would be the hands-on approach of setting up an example domain name with DNSSEC. So when setting up DNSSEC to secure your domain name and its DNS records, the first new record type we will create is a DNS key record. In fact, you will have two DNS key records. One will be a private key and the other a matching public key. In DNSSEC terminology, this is called a key signing key. Think of this like a master key for the landlord of an apartment building that will be used with all of the domain names or tenants of your DNS server. You will often see this abbreviated in DNSSEC documentation as the acronym KSK. But you will notice there are no commands shown on the slide or the slides that immediately follow to generate these keys. We'll get to the specific commands for a few different DNS server examples a little bit later, but for now the goal is to introduce you to DNSSEC's concepts first. So next, we are going to create another pair of DNS key records. Again, we will have a private and a public key, but this time the key pair is only for a specific domain name, Zimbra.example. On DNS servers, a domain name is called a zone. Since this key pair will only be used for the Zimbra.example zone, this key pair is known as a zone signing key. You can think of a zone signing key like a set of keys that get you into a specific apartment in an apartment building as a tenant. We also need this new zone signing key for Zimbra.example to be signed by our key signing key so as to establish trust between the two keys. Now this signature is going to be stored in another new record called an RRSIG or resource record signature as part of the Zimbra.example zone. And you can think of the RRSIG record like a tenant in an apartment building trusting their landlord to use the landlord's key to enter for, say, performing maintenance. Now we need the individual DNS records for Zimbra.example to be signed using our zone signing key. Now, this is an important part of what allows anyone who queries for these DNS records to use DNSSEC to authenticate that the DNS records can be trusted and have not been tampered with in transit. To make this happen, all of the individual DNS records for Zimbra.example will be grouped together first by record type, then by name. So if you had two MX records, and they share the same name, in this case, Zimbra.example, then both of those MX records would be placed into a single group together. But if you just had a single MX record, then that one MX record would essentially be in a group all by itself. The same grouping process happens for all of the other record types too, like your SOA, your NS, A, Quad A, pointer, text, CNAME, and serve records. Once these groups are created, then your zone signing key will sign each of these individual groups. The end result will be a unique signature for each group that is stored in the Zimbra.example zone as new RRSIG records, or again, resource record signatures. And finally, to finish things up for Zimbra.example, INSEC or Next Secure records are automatically created for each individual DNS record that exists for our Zimbra.example domain name. The purpose of an INSEC record is to provide pointers to the next record in the zone. So if we have an SOA record for Zimbra.example, its INSEC record would point to ftp.zimbra.example, as this is the next record alphabetically that appears in the zone. Likewise, the INSEC record for ftp.zimbra.example would then point to mail.zimbra.example, followed by an INSEC record that points to www.zimbra.example, until it finally loops back to the start, pointing again back to that same SOA record for Zimbra.example. Now you may be wondering what purpose an INSEC record serves in real-world use. So if you recall from earlier in the webinar, one of DNSSEC's design goals is its ability to provide a name, prove that a name definitively does not exist. So this basically means that an adversary looking to use DNS cache poisoning to inject a new fictitious DNSA record, like support.zimbra.example, would fail. This is because none of the INSEC records would point to this fictitious support.zimbra.example name created by the adversary, so it would be rejected and ignored. Now, in DNSSEC terminology, this is called authenticated denial of existence, which is basically a fancy way of saying that the INSEC records can be used to definitively prove whether a name returned in a DNS answer is legitimately part of that zone or not. After all of these INSEC records are created, just like we saw on the prior slide, new RRSIG, or again, resource record signatures, are created for each of these different INSEC records too, using the same zone signing key we used earlier. These RRSIG records are used to prove that the INSEC records can be trusted and have not been tampered with in transit to a DNS caching server. But what if a client wanted to discover every possible DNS record you have set up in your zone for Zimbra.example, better known as zone walking? Thanks to the INSEC record, this looks pretty easy, right? Well, you would be correct, and this is the downside to INSEC records, in that it makes it trivial for anyone to discover every DNS record set up within your zone. But bear in mind that DNS was never designed to store confidential information, but some organizations do depend on preventing zone walking to avoid discovery of hidden names in their DNS zone. Perhaps these are intended for internal employee use, for example. Fortunately, a solution was built into DNSSEC to avoid this type of information disclosure. And that solution is to use what are called INSEC3 records instead. Now, INSEC3 records work identically to the INSEC records we just looked at, but with one important change. The names included in the INSEC3 records are all hashed, so all, as you can see on the slide, but they are now far less readable and make zone walking very difficult. The generated hashes are normally much longer but have been truncated to, of course, fit on the slide. So if this is an INSEC version 3 record, are there any other INSEC versions available too? Well, the answer is no. There are only the 2 versions currently supported in DNSSEC, and it is at your discretion which of those you would like to use. But most DNSSEC deployments tend to use INSEC3. Its hashing method for preventing zone walking is not unbreakable, but it is typically sufficient to keep out all but the most determined individuals. There have been some efforts at creating a follow-up INSEC version with even more robust hashing of names, but these efforts have not left the proposal stage yet. However, the extensible nature of DNSSEC keeps this option open for the future. So after creating these many different records in our zone, is our DNSSEC setup for Zimbra.example now complete? Well, almost, but we need to finish one essential step that involves completing what is called the DNSSEC chain of trust. So at this stage, we have successfully created a chain of trust within our DNS server, starting with the key signing key that trusts the zone signing key for each domain name, such as Zimbra.example. Then each zone signing key trusts the individual DNS resource records within its respective zone. These trust relationships are expressed as signatures stored in our RSIG records, as discussed in the prior slides. But in its current form, these trust relationships only exist in an isolated silo within your DNS server. So how do we get other DNS servers on the internet to trust these keys within your DNS server? The answer is that we use another of DNSSEC's new record types called a DS, or delegation signer record. So at the top of the slide, we have the internet DNS root, indicated by the single period. This includes a self-signed key, since the internet root has no parent. This self-signed key is periodically changed by the international organization ICANN through a very elaborate key signing ceremony. Next, the internet root contains delegation signer, or DS records, indicating that the internet root trusts each of the domain registries that manage the top-level and country code domains, like .com, .nl, .example, .net, and .us in this illustration. Further down the diagram, there's another DS record that delegates trust from the .example registry to your DNS server that hosts the Zimbra.example zone. This is the DS record that we will set up next, and it will be provided to your domain register, allowing a complete chain of trust to be created from the internet root all the way down to your individual DNS records for Zimbra.example. This means that when a client on the internet performs a DNS query for the Zimbra.example domain name or any of its subdomains, it is going to use this DS record that you will be creating to authenticate your name server and that it is authorized to answer queries for Zimbra.example. Now, additionally, when a client on the internet receives an answer to a query from your DNS server, that client is automatically going to receive the appropriate RRSIG records too that we created in the earlier steps. The client's going to follow this with another query for your public key signing key and your public zone signing key, both from your DNS server. Using these public DNS key records, the client can then fully authenticate that the RRSIG records received are authentic and have not been tampered with in transit. So the client will know that the answer to their DNS query can be trusted. But consider this. What if you had DNSSEC set up for Zimbra.example on your DNS server, but had failed to add the DS record to your domain register? Well, in that case, nothing too bad would happen. It would essentially mean that even though you have DNSSEC on your domain names, none of the outside clients on the internet are going to acknowledge this. But looking at it from the other way around, if you've set up the DS records at your domain register, but have failed to set up DNSSEC on your own individual domain name server, this is going to cause you many problems. So that is not something you want to do. The takeaway here is that it's important to secure each domain name with DNSSEC on your own server first, and then at about the same time, add its DS record at your domain register. Now, before we get into the specific commands that need to be run to set up DNSSEC on the different DNS servers, it is also important to cover some prerequisites that must be met on your network and host-based firewalls before setting up DNSSEC for the first time. Now, DNSSEC responses are going to be larger than traditional DNS packets on your network, so it is important that your firewalls are configured correctly to avoid blocking these larger packet sizes. Specifically, ensure that your firewall is allowing inbound and outbound traffic on port 53 for your DNS servers. Many firewalls traditionally limit DNS traffic just to UDP port 53 only. Now, if your firewall limits UDP packets to 512 bytes, which tends to be the default, you will need to allow packets of at least 4,000 bytes or 4 kilobytes in size to account for those larger DNSSEC replies. Now, if you have DNS application level or have a application level gateway enabled, you're also going to need to disable it. Many of these DNS ALGs do not allow for the larger DNSSEC packet sizes. And finally, if you have fragmentation of UDP packets disabled on your firewall, you need to enable it. Because of the larger DNSSEC packet sizes, these packets are often broken into multiple parts, and having fragmentation disabled will cause packets to be dropped, thereby breaking your DNSSEC implementation. So any earlier advice you may have received about disabling fragmentation is often well-meaning, but unfortunately misguided, as this has never really offered any real-world security benefit. So now that you have a good understanding of the DNSSEC concepts and how it works, we're ready to take a look at the actual commands needed to set up your DNS server for DNSSEC. Now, given the time constraints here, I'm going to cover just 4 of the most popular options for configuring a DNS server. 2 will be using a GUI or graphical user interface, such as cPanel and Plesk, and 2 are going to be for the command line with PowerDNS and Bind. Now, if your preferred DNS server is not listed on the slide, check your vendor's documentation for DNSSEC support. Most DNS vendors have long had DNSSEC support built in, so chances are good that your favorite DNS vendor supports it too. So to get started with using DNSSEC and cPanel, you're going to need to navigate to the page for the domain to be secured with DNSSEC. And next, you're going to select the zone editor and click the DNSSEC button in the row of domain or the row of the domain to be secured. And then you're going to click the Create Key button. And then you're going to basically get a pop-up box, and you need to click the Customize button. Then use the options shown on the slide for the key type, the algorithm, and the status. Now, if you do not use the Customize button, cPanel is going to create a very weak DNS key record, so it's important to ensure this is set correctly, again, using this Customize option. Then click the Create button, and the DS or delegation signer records will be displayed to you. We'll provide just one of these DS records to your domain register, and I'm going to cover how to do this on a later slide. And to get started with DNSSEC and Plesk, you're going to need to navigate to the Websites and Domains page, select the domain to be secured with DNSSEC, then click DNSSEC, followed by the Sign the DNS Zone option. Now in the Key Signing Key section, set the options as you see on the slide. But be aware that the rollover period you set for the key signing key determines how frequently you will need to update the DS or delegation signer records for this domain name at your domain register. Typically, this should be a pretty long period of time, of let's say at least 5 or more years, but it could be even longer if you would like. In the zone signing key section, set the same options as you used for the key signing key section, but with a shorter rollover period, such as 6 or 12 months. You could even go shorter if you wish, but I wouldn't get carried away. Anything less than a month or two is pretty extreme. Plus will take care of the zone signing key rollovers automatically for you within your DNS server. So it is recommended to use a much shorter period here. Then just simply click the OK button, and the DS or delegation signer records are going to be displayed for you. And again, we're going to provide just one of these DS records to your domain register. And with PowerDNS, it's distributed as 2 different packages. In one package is the authoritative DNS server only, and then the other package is the recursive DNS server only. So we're going to cover the authoritative server first on this slide. So to set up DNSSEC with PowerDNS from the command line, you will first basically need to run the pdnsutil rectify zone command you see in step 1 by substituting the domain name.tld placeholder with the domain name you want to secure with DNSSEC. What this is going to do is it's going to prepare that domain name zone with some extra values that will be needed for DNSSEC. Next, you're going to need to run the pdnsutil secure zone command in step 2. Again, substituting the domain name.tld placeholder text with your domain name. This is what actually basically signs your zone with DNSSEC. Then, if you wish to use INSEC3, which I recommend that you do also consider doing, you first need to create a randomly generated seed value. Now, I suggest generating a 512-character random string using an online tool of your choice, but if you want to do this all from the command line, I've included a bash command that you can do to basically accomplish the same thing. Next, create the seed value with the echo, next also include that seed value with the echo command that you see on the slide, substituting the random string placeholder text with the 512-character string you created in the prior step. This is going to output a single 16-character hash value, and this is actually what we're interested in. So we're going to create the INSEC3 records for your domain name using the pdnsutil set INSEC3 command shown at the bottom of the slide. All you have to do is substitute the domain name.tld placeholder with your domain name and the hash string placeholder text with the 16-character hash that you created in the prior step. So to finish, we're going to run the pdnsutil rectify zone command again, and we're going to substitute, of course, your domain name as shown in step 4 there. Then we're to display the DS delegation signer records. We're going to basically use the pdnsutil show zone command, again substituting your domain name in place of the domain name .tld text you see. And when you're using the PowerDNS recursive server, because again, remember this is a separate server, separate package from the PowerDNS authoritative server, you're going to basically need to do a fairly simple change here. You're going to need to open up your configuration file. It's typically in the /etc/recursor.config file. And there's 2 settings that need to be set as shown on the slide. The DNSSEC equals validate setting is basically going to require PowerDNS to attempt to use DNSSEC for all queries and to reject any DNS answers that fail DNSSEC validation. There are some weaker modes that you can select here, but this is really the best one to use because, again, it enforces it both for queries you're sending as well as queries you're receiving. The DNSSEC log bogus setting is also recommended, as what it does is it turns on logging in PowerDNS to track any domain names that fail DNSSEC validation, typically to the system messages log. This can be really helpful for troubleshooting if you need to easily spot the domain names of other domains basically that are failing DNSSEC. Now for bind, there is a setting that determines if DNSSEC validation is used for recursive queries, or in other words, DNS queries that bind sends to other DNS servers on the internet. If you're using bind 9.11 or later, this setting is already enabled for you by default, which is great news. You don't have to do anything. But if you're using a bind version earlier than 9.11, then you will need to enable it manually in your bind configuration file within the options section as shown on the slide. Once enabled, this again is going to require bind to use DNSSEC validation for all queries and to reject any DNS answers that fail DNSSEC validation. Full support for DNSSEC was added in Bind version 9. However, very recent versions of Bind, starting with 9.17, have made securing domain names with DNSSEC considerably easier. So I recommend that you upgrade to at least Bind 9.17, if not the latest stable version available. If you're using at least version 9.17 or later, to secure a domain name with DNSSEC, you need only edit your bind configuration file, typically in the etc named directory, and you're going to add the DNSSEC-policy default setting as shown on the slide. But if you're using an earlier Bind 9 version, you're going to need to instead refer to the URL at the very bottom of the slide for an in-depth walkthrough of how to manually configure DNSSEC for a domain name. Take my word for it, it is definitely worth upgrading your Bind server rather than the manual configuration step. Then have Bind reload its configuration using the RNDC reconfig command, or just restart the name's D service. Now for reviewing the generated DS or delegation signer records, it is a bit trickier in Bind than with other DNS servers, since the specific steps will vary a little bit based on the Bind version you're using. But I've included a URL to the Bind documentation so that you can select the method your DS records, to select the correct method based on your Bind version to view your DS records. So after you've secured your domain name with DNSSEC on your preferred DNS server, most DNS servers are going to output the DS or delegation signer records on screen that you will need to provide to your domain register. Now, this is a required step, as again, remember, as part of that DNSSEC chain of trust, this is what allows other DNS servers on the internet to trust your keys on your DNS server. So we see a couple of versions of the DS record for your domain name. Now, each of these is using a different encryption algorithm and hash, and these are going to look pretty cryptic at first glance. So let's break these down into what you need to know. We're going to be using just a single DS record that will be provided to your domain register. So to simplify this discussion, we're going to focus on the first DS record listed on the slide that contains a SHA-256 digest. Now, the reason that we will ignore the DS record with the SHA-384 digest is because support for SHA-384 in DNS clients is not quite universal yet on the internet. Plus, the SHA-384 hash creates considerably more computational work for both DNS servers and clients to use. So in this DS record, the highlighted 26214 number is what is called a key tag. Think of this like a unique numerical ID that identifies the public key for your domain name on your DNS server. This key tag will be a different number for every domain name that you secure with DNSSEC. It's going to offer a required hint to DNS clients who send queries for the Zimbra.example domain name of which of the many different DNS key records on your server that the client should use. The next number in the DS record is 13, and this refers to the algorithm number, or encryption algorithm. When DNSSEC was first created, the authors anticipated that as technology progressed and got better, encryption algorithms would eventually become too weak to keep DNSSEC records secure. So they built in support to have a near unlimited number of encryption algorithms that could be added over time without needing to completely re-architect the DNSSEC standard every single time they want to add a new algorithm. At the bottom of the slide, you're going to see a partial list of some of the commonly used algorithms along with their ID number. Many older DNSSEC deployments still use encryption algorithms based on RSA. But it's important to avoid using any of these RSA options, as this opens your DNS server up to being an unwitting participant in a distributed denial of service reflection attack, thanks to the large RSA key sizes. For all new DNSSEC deployments, stick with algorithm 13. This is the algorithm for elliptic curve digital signature algorithm, and one of its main advantages is its smaller key sizes provide exponentially stronger security than their comparable RSA keys with the same key size. This means that DNSSEC responses sent from your DNS server are going to basically be smaller, and making you far less attractive to being an unknowing participant in a denial service reflection attack against someone else. The next number in the DS record, that is 2, is the digest type. Now at the bottom of the slide, you're going to see a small table showing you the different digest type options available. SHA-1 is simply too weak to use and should never be considered. And SHA-384, again, is going to prevent compatibility problems with DNS clients and servers. So really, SHA-256 is your best option here. And finally, the last highlighted item in the DS record is the hash, also known as the digest. Your DNS server creates this unique hash for each domain you secure with DNSSEC, and this corresponds to one of the DNS key records on your DNS record, or DNS server. So now that you basically understand the contents of what a DS record provides, what you need to do is you need to provide these 4 bits of information: the key tag, the algorithm number, the digest number, and the digest to your domain register where your domain name is registered. For domain registers, this basically involves logging into a control panel for your domain name, locating the DNSSEC or DS record feature, then copy and pasting in these 4 values. Now, if you manage a lot of different domain names, it is unfortunate that this is a manual process, but there are some proposed standards in the works that promise to automate this step by allowing your DNS server to basically upload the DS records information directly to a domain register. Well, several domain registers also offer an API or application programming interface that can basically be used to submit DS record information in a somewhat more automated manner. And once your domain register has this information, they will automatically relay it on your behalf to the appropriate domain registry, at which point it completes the DNSSEC chain of trust. And this is going to allow all other DNS servers on the internet that support DNSSEC to trust the keys on your DNS server too. Let's look at a few best practices for DNSSEC. Now, DNSSEC has a strong reliance on an accurate system clock on your DNS server. This is because each of your domain names that is secured with DNSSEC is going to have RRSIG records that have expiration times. Now, your DNS server relies on an accurate system clock, so it knows when to recreate these RRSIG records periodically. And this is an automatic process. If your DNS server's clock is considerably out of sync with the correct time of, say, other DNS servers, it's going to cause those other DNS servers to incorrectly discard your RRSIG records as being expired and invalid. And this would, of course, break your entire DNSSEC validation. But so to avoid this, you're always going to want to install a time synchronization service like NTP or CroneyD or similar to keep your DNS server's system clock set reasonably close to the correct time. A few seconds or minutes of difference is unlikely to cause much harm, but the closer to the exact time your system clock is on your DNS servers, the better. And a common mistake is to run both your authoritative and your DNS resolver servers on a single VM or physical server. This is just a bad idea, and it's going to make cache poisoning by adversaries even easier. As readily accessible as VMs are today, there's really no reason to do this. So it makes sense to separate these different responsibilities equally. Now, it's going to basically depend on your environment and your sensitivity to risk, but you could actually take this a step further, and you could segment your servers by having multiple DNS resolvers. Perhaps one might be dedicated just for your servers, and you might have another DNS resolver dedicated to your end users. The thinking there is that if DNS cache poisoning happens on one, it doesn't affect the other. So to wrap things up, here's some key takeaways to keep in mind. Before deploying DNSSEC, check your firewall settings carefully, as discussed in the earlier slide. A misconfigured firewall is going to make it very difficult for you later to troubleshoot DNSSEC problems, and it can consume a lot of your time to identify and fix those problems. Make it a priority to keep your DNS server versions up to date, regardless of the DNS server vendor you use. New vulnerabilities are regularly discovered in each DNS server, and staying up to date is not only going to keep you safe, but it's generally going to make administration easier for you too. And when you're first getting started with DNSSEC, it is often useful to practice securing an inactive domain name first. This is a low-pressure method allowing for you to safely make mistakes without causing any service outages on your production domains. And when you feel confident with the process of securing a domain with DNSSEC, then, of course, move forward with securing your production domains as your next priority. And always use strong algorithms and hashes when selecting the right DS record information to provide to your domain register. At present, algorithm number 13, the elliptic curve digital signature algorithm, is the best algorithm to use, along with the digest type number 2, which is SHA-256. This, of course, will eventually change as newer and more efficient algorithms become available, so periodically review the setting at least once every few years to stay informed and updated on best practices. So thank you so much for attending today's webinar. I hope you found it educational and appreciate your time attending. If you would like to reach out to me directly with any additional questions or feedback, my contact information is included on the slide, but also included on the slide are some useful online tools. The first is a readiness tool that you can use to test your firewall for DNSSEC. Also included are some testing tools that you can use to validate your DNSSEC configuration for your domain names. These tools are really important to use as you're first getting started because they can help you quickly spot any mistakes to avoid later service outages. And I look forward to seeing you on the next webinar that will be all about TLS and the DANE security standards.
Thank you, Randy. Thank you, everyone, for your attendance. Bye-bye.
Bye, everybody.